Okay, this is section 2.4, Symmetry. Symmetry. The idea of symmetry is that one half of an object looks like the other half of the object. For example, if we have the graph of the parabola y equals x squared, which we've graphed a few times before, the left half of the graph looks like the right half of the graph. So below I have the graph of y equals x squared. So again, this side looks like this side. In mathematics, we have three basic types of symmetry. The parabola actually showed one of them. So number one, we have symmetry with respect to the x-axis. Number two, symmetry with respect to the y-axis. And number three, symmetry with respect to the origin. There's actually a fourth symmetry, but for some reason our book chooses not to do it. So we want to be able to test for symmetry with respect to each one of those things, x-axis, y-axis, and origin. We'll draw pictures in each case and then formalize what the tests are in terms of doing algebraic manipulations. So note, the phrase with respect to occurred quite often. For that reason, we will use the abbreviation WRT for the phrase with respect to. It will save us a lot of writing. So WRT is going to stand for with respect to. Okay, our first type, symmetry. Symmetry with respect to the x-axis. Again, remember WRT with respect to. Graphically, symmetry with respect to the x-axis looks like this. Okay, notice this thing is not a function. Okay, it is a relation, but it's not a function. So the idea is if you fold along the x-axis, the pieces will coincide. So if you fold along the x-axis right here, this piece and this piece will coincide. We make this formal with, okay, we're going to have the definition. Okay, before we make the definition, look at x equals 1 has y 1 and y negative 1. If x is 2, I get y is positive 2 or negative 2. So for each y, I've got a plus y and a negative y. So we're going to make this formal with definition. 2 points are said to be symmetric with respect to the x-axis if and only if they satisfy the following. Number 1. They have the same x-coordinate. Number 2, their y-coordinates are opposites or additive inverses of each other. Okay, this definition of symmetry with respect to the x-axis is also going to lead to the test for symmetry with respect to the x-axis. So the test is what we'll apply whenever we're given an equation. And notice, since symmetry with respect to the x-axis is not a function, we're talking about relations in general here. So the test for symmetry with respect to the x-axis. Given an equation x and y, if replacing y by negative y produces an equivalent equation, then the graph of the equation is symmetric with respect to the x-axis. Notice, replace the other variable by its opposite. So symmetry with respect to the x-axis, replace y with negative y, and see what happens. Before doing examples, we present the definitions and tests for symmetry with respect to the y-axis and the origin. That way we can lump them all together. So we just did the x-axis, symmetry with respect to the y-axis. Okay, graphically, symmetry with respect to the y-axis looks like this. Okay, again, the idea is if you fold along the y-axis, the pieces will coincide. Again, now notice this particular value of y, 2, has x to be 2 and x to be negative 2. This value of y equals 3 has positive 3 for x and negative 3 for x. So it looks like each y value has a positive x and a negative x to go with it. Notice this one is a function. Now it doesn't mean that everything that's symmetric with respect to the y-axis is a function. It doesn't have to be. This one just turns out to be. So we're going to make this formal with the definition. Okay, now again, notice each y had an x and a negative x to go with it. So definition. 2 points are said to be symmetric with respect to the y-axis if and only if they satisfy the following. Number one, they have the same y coordinate. And number two, their x coordinates are opposites or additive inverses of each other. Now, just like the definition of symmetry with respect to the x-axis led to a test, this definition will also lead to a test for symmetry with respect to the y-axis. So the test for symmetry with respect to the y-axis is, given an equation in x and y, if replacing x by minus x produces an equivalent equation, then the graph of the equation is symmetric with respect to the y-axis. So again, you replace the other variable by its opposite. So if you're testing for symmetry with respect to a particular axis, replace the other variable with its opposite and see what happens. If you get the same equation or equivalent equation, you have symmetry. If you don't get an equivalent equation, you don't have symmetry. Okay, we got one more symmetry to go. Symmetry with respect to the origin. So graphically, symmetry with respect to the origin looks like that. Okay? Notice this one is a function, but it doesn't have to be. The idea is if you rotate the graph 180 degrees, the graph will look the same. Or if you actually stand on your head and look at it, the graph will look the same. So now notice, I've got a point 1, 1, negative 1, negative 1. I've got what looks like 3 and 1.5, negative 3 and what looks like negative 1.5. Both x and y are changing signs. So we're going to make this formal with a nice little definition of symmetry with respect to the origin. Definition: 2 points are said to be symmetric with respect to the origin if and only if they satisfy the following. Their x coordinates are opposites or additive inverses of each other. And number two, their y coordinates are also opposites or additive inverses of each other. So notice that both variables are changing signs. So this definition is going to lead to the test for symmetry with respect to the origin. Remember, for the coordinate axes, to test for symmetry, you replaced the other variable with its opposite. So the test for symmetry with respect to the origin. So given an equation in x and y, if replacing x with negative x and y with negative y produces an equivalent equation, then the graph of the equation is symmetric with respect to the origin. So for the origin, it's kind of like you combine the other two tests. So remember, to test for symmetry with respect to a particular axis, let the other variable be 0. To test for symmetry with respect, let the other variable be the opposite. To test for symmetry with respect to the origin, replace both variables with their opposites. Let's try some examples. Determine if the graph of each equation is symmetric with respect to part A, the x-axis, part B, the y-axis, part C, the origin. So it's x-axis, y-axis, origin. So here's our first one. I got 3x plus 6y equals 12. Okay, this is a line. This is actually a line. So for part A, we're testing for symmetry with respect to the x-axis, so replace y with negative y. I'll have 3x plus 6 times negative y equals 12. Okay, 6 times negative y is minus 6y. So we have 3x minus 6y equals 12. Is this equivalent to the original equation? I don't think so. So it's not equivalent to the original equation. So we don't have symmetry with respect to the x-axis. For part B, we're doing symmetry with respect to the y-axis. So replace x with negative x. So I'm going to have 3 times negative x plus 6y equals 12. That gives us negative 3x plus 6y equals 12. Now, is this the same thing as the original one? No. So it's not equivalent to the original equation. So we do not have symmetry with respect to the y-axis. And so we got the origin, part C. To test for symmetry with respect to the origin, replace x with negative x and y with negative y. So we're going to replace x with negative x and y with negative y. So we'll have 3 times negative x plus 6 times negative y equals 12. That gives us negative 3x minus 6y is 12. Even if you make it look like 3x plus 6y, you'd have to change all the signs. That gives you 3x plus 6y equals negative 12, which is not the same. So we don't have symmetry with respect to the origin. We didn't have any symmetries. Now here's a little fact that might help you out for some things if you're in a rush. If in the three symmetries, x-axis, y-axis, and origin, if you get two of them to be yes, that is symmetric, the third one has to be. But now just because you have two of them no, it doesn't mean the third one has to be. This was just a nice coincidence. Here's our second example. I've got 2x squared minus 3y cubed equals 11. Okay, now again, we're doing in part A, symmetry with respect to the x-axis. So replace y with minus y and see what happens. So I have 2x squared minus 3 times negative y cubed equals 11. Okay, if you cube negative y, you end up with negative y cubed, and minus times minus will be plus. So you have 2x squared plus 3y cubed equals 11. That does not appear to be equivalent to the original one. So it is not symmetric with respect to the x-axis. Okay, part B, we were testing for symmetry with respect to the y-axis. So replace x with negative x. Okay, for the y-axis, replace x with negative x. So I have 2 times negative x squared minus 3y cubed equals 11. If you square negative x, you'll get a positive x squared. Minus times minus is plus. So I end up with 2x squared minus 3y cubed equals 11. Notice that's the same as the original. So it's equivalent to the original equation. So we do have symmetry with respect to the y-axis. Now if you think about it, remember I told you a little while ago that if you get two of them to be yes, the third one has to be. I've got a no and a yes. That means the origin has to be a no. But if we go through the process, so for symmetry with respect to the origin, we replace x with negative x and y with negative y. So when we do that, we're going to get 2 times negative x squared minus 3 times negative y cubed equals 11. Now, again, if we square negative x, it becomes positive x squared. Cubing negative y gives me a minus on the y cubed, and minus times minus is plus. So I've got 2x squared plus 3y cubed equals 11. That's not equivalent to the original. So it is not symmetric with respect to the origin. Okay, again, remember, for testing symmetry with respect to an axis, let the other variable be 0. For the origin, 0. Why do I keep saying that? Replace the other variable with its opposite. For the origin, replace both variables with their opposites. Number 3. I have y equals negative 5 over x. Okay, y equals negative 5 over x. Okay, for part A, we're doing symmetry with respect to the x-axis. So replace y with negative y. I have negative y equals negative 5 over x. Okay, to make the comparison to y equals, I'm going to multiply both sides by negative 1. That way I'll have a positive y on the left. If I multiply both sides by negative 1, I get y equals 5 over x, which is not equivalent to the original. So that means I do not have symmetry with respect to the x-axis. For part B, we were doing symmetry with respect to the y-axis, so we replace x with negative x. So we'll have y equals negative 5 over negative x. Okay, minus over minus is plus, so we'll get y equals 5 over x. That's not equivalent to the original equation. So we do not have symmetry with respect to the y-axis. Now again, just because you get two no's, that doesn't force the third one to be a no. If we'd gotten two yeses, that would force the third one to be a yes. Okay, so let's go through the test for symmetry with respect to the origin. Now I'm going to replace x with negative x and y with negative y. So I'm going to have negative y equals negative 5 over negative x. Okay, on the right-hand side, negative over negative is positive, so I have negative y equals 5 over x. Now again, to solve it for y, to make it look like y equals, I'll multiply both sides by negative 1. So I'll end up with y equals negative 5 over x, which is equivalent to the original equation. So that means I do have symmetry with respect to the origin. Let's try some graphing. Determine if each graph is symmetric with respect to part A, the x-axis, part B, the y-axis, part C, the origin. And remember, to determine symmetry with respect to the x-axis, the idea is if you fold along the x-axis, pieces coincide. For the y-axis, if you fold along the y-axis, pieces coincide. And for the origin, if you rotate through 180 degrees, do you get the same picture? Or if you stand on your head, do you get the same picture? So again, I've got x-axis symmetry, y-axis symmetry, and origin. So here's my first one. Okay, it looks like a W. Okay, it looks like a W. Okay, for part A, symmetry with respect to the x-axis. If you fold it along the x-axis, will the pieces coincide? No. For symmetry with respect to the y-axis, if you fold it along the y-axis, will the pieces coincide? Will this match up with this? Yes, it will. Okay, for symmetry with respect to the origin, if you rotate it through 180 degrees, will it look the same? No. If you rotate a W through 180 degrees, it looks like an M, so you don't have any symmetry there. This is where actually drawing it on paper and doing the folding might help. Also, it's kind of an art skill, not a math skill. Number 2, I've got this oval thing, an ellipse. Okay, for part A, symmetric with respect to the x-axis. Now again, if I fold it along the x-axis, will the top half of the ellipse match up with the bottom half? Yes. For part B, symmetric with respect to the y-axis. If I fold along the y-axis, will the left side of the ellipse match up with the right side of the ellipse? Yes. And for symmetric with respect to the origin, if you rotate it through 180 degrees or stand on your head, you get the same thing. But again, remember, if you get 2 yeses, the third one has to be a yes. Okay, let's focus on functions now. So our next topic for this section 2.4, whoops, got one more. Look at examples. Okay, for each point, find the coordinates of the point that is symmetric to it with respect to the x-axis, part B the y-axis, part C the origin. So I'm going to give you a point, and you're going to give me the coordinates of the point that has the symmetries with respect to x-axis, y-axis, and origin. Okay? So it kind of comes down to, do you remember which one changes its sign? So here's my point, negative 623. Okay, negative 623. For part A, the x-axis, remember, you change the sign of the other variable. So x stays the same, and y changes sign. So it's going to be negative 6, negative 23. Those 2 points are symmetric with respect to the x-axis. For part B, the y-axis. Okay, remember, the other variable changes sign. So x changes sign, and y stays the same. So going back to our original point, I'm going to get 623. So the point is 623. So negative 623 and 623 are symmetric to each other with respect to the y-axis. Part C, the origin. Remember, both of them change sign. X changes sign and y changes sign. So I'm going to get my point is going to be 6, negative 23. So negative 623 and 6, negative 3 are symmetric with respect to each other, which means symmetric through the origin. Let me try again. Negative 623 and 6, negative 23 are symmetric with respect to the origin. There we go. And let's try one more. I've got the point negative 9 and negative 200. Okay, for part A, we're looking for the point that's symmetric with respect to the x-axis. So again, remember, the other variable changes sign. So x stays the same, and y changes sign. So it's going to be negative 9, 200. So negative 9, negative 200, and negative 9, 200 are symmetric with respect to the x-axis. For part B, okay, the y-axis. Okay, remember, x changes sign, y stays the same. So my point is going to be 9, negative 200. And now for the origin, remember for the origin, they both change sign. So x changes sign, y changes sign. So I'm going to have 9, 200. Okay, remember, for the symmetry with respect to an axis, the other variable changes sign. For symmetry with respect to the origin, both variables change sign. Okay, now let's look at functions. So part 2, even and odd functions. Now, these are functions. We now look at relating the idea of a symmetry to functions. Okay, not just relations, but functions. Remember that a function must pass the vertical line test. That means that no vertical line is allowed to intersect the graph of a function in more than one point. So for functions, there are only two possible symmetries. Number one is symmetry with respect to the y-axis. And number two, symmetry with respect to the origin. Remember, the symmetry with respect to the x-axis, if you fold along the x-axis, the pieces coincide. That says that a vertical line is going to pass through at least 2 points, maybe more. So these two symmetries, symmetry with respect to the y-axis and symmetry with respect to the origin, are going to lead to the notion of even and odd functions. So this leads to, again, the symmetry with respect to the origin and symmetry with respect to the y-axis leads to definition. Let f be a function. Okay, so I've got a function. Then, number one, f is called even if and only if f of negative x equals f of x for all x in the domain of f. Kind of like even functions, ignore the minus signs. That's what it amounts to. And for number two, f is called odd if and only if f of negative x is equal to the negative of f of x for all x in the domain of f. It's kind of like an odd function factors out the minus sign. Okay, some notes on this. So notes on even and odd functions. Number one, a function is even if and only if it is symmetric with respect to the y-axis. Okay, the classic example is f of x equals x squared. Okay, that is the classic example. Number two, a function is odd if and only if it is symmetric with respect to the origin. Okay, now most students will think, oh, f of x equals x cubed is the classic example. There's actually one that's much simpler, just f of x equals x. So for the classic even, it's f of x equals x squared. For the classic odd, it's f of x equals x. Number three, a polynomial function is even if and only if all of the exponents on the variables are even. That's kind of where the name came from. Now remember, 0 is an even number, and x to the 0 power would be 1. So that means there would be no x term. And number four, a polynomial function is odd if and only if all of the exponents on the variables are odd. Remember, 1 is odd, and if you don't see an exponent, it's understood to be 1. Now if you think about it, that means most polynomial functions are neither even nor odd, because they have a mixture of even and odd exponents on the variables. Number five, when given a formula for a function to determine, that should say if it is even, odd, neither or both, find f of minus x and compare it to the original function. Okay, so you always evaluate f of negative x when you're asked about even, odd, neither or both. Part A, if f of negative x and f of x are the same, then the function is even. If f of negative x is the opposite of f of x, meaning all the signs changed, then the function is odd. Now if it turns out neither one of those happens, then it's neither. If both of them happen, then it's both. Most garden variety functions that are just lying around in the street are neither even nor odd. Let's try some examples. Determine if each function is even, odd, neither, or both. So this is great multiple choice. And notice I've covered all possibilities, even, odd, neither, or both. So here's my first one. I have f of x equals 3x plus 12, your classic line. Can you remember, whenever you're determining whether or not a function is even, odd, neither, or both, evaluate f of negative x. So f of negative x is 3 times negative x plus 12, which is negative 3x plus 12. This is not the same thing as the original function. So it's not f of x, and it doesn't equal minus f of x. In order to be the negative of f of x, all of the signs have to change. Only one of the signs change. So this is neither even nor odd. Number 2. I have f of x equals 4x over x squared plus 10. Okay, once again, evaluate f of negative x. So I have 4 times negative x over negative x squared plus 10. Okay, in the numerator, 4 times negative x is negative 4x. In the denominator, if you square negative x, you get positive x squared. So I have negative 4x over x squared plus 10. Notice, this is the opposite of f of x. I can factor out that minus sign and put it in front of the fraction. So there, I've put the minus sign in front of the fraction. So I now have the negative of f of x. That means it's odd. Okay, now again, remember, the minus sign can come in front of the fraction, and then the fraction, remember, is the original function. Number 3. F of x is equal to negative 5 over 7x squared plus 10. Okay, once again, evaluate f of negative x and see what happens. I'm going to have negative 5 over 7 times negative x squared plus 10. If you square negative x, you get positive x squared. So I'm going to have negative 5 over 7x squared plus 10. That's the original function. That's equal to f of x. That's even. Okay, the function is even. Number 4. I have this graph. Here's my graph of f of x. Now, first of all, be sure that it is a function. Make sure that it does pass the line test. Now, remember, we're only looking at 2 symmetries, y-axis and origin. If you fold along the y-axis, will the pieces coincide? Yes. If you rotate through 180 degrees, will it be the same graph? No. So it's even. So that means, symmetry to the y-axis, that was even. Okay? Number 5, I have this funny looking graph. Okay, now for even, I want to fold along the y-axis and see if the pieces coincide. No, if I fold along the y-axis, this doesn't match up with anything. If I rotate this through 180 degrees, this point that was down here is suddenly up here. So that's not the same either. So I don't have symmetry with respect to the y-axis, I don't have symmetry with respect to the origin. So it's neither even nor odd. And let's try one more. I got this funny looking nest. I believe this may have been one of our pictures when we first began talking about symmetry. Okay, if you fold along the y-axis, this piece has nobody to match up with. If you rotate this picture through 180 degrees, okay, this piece will become that piece. It is symmetric with respect to the origin. That means it's odd. Okay, now this is really not a vertical line segment here, it's just the resolution of the software made it look that way. That's the end of section 2.4.